This is a continuation of a tutorial on monotransformers. Here I will talk about monotransformers built with functor composition. So these are transformers where the base monad L and the foreign monad M are combined either as composing inside, like this, where the base monad the foreign monad is inside, or outside. The foreign monad is outside, or base monad is inside. So I call them composed outside and composed inside transformers. While the monads that have these transformers are quite different, so the option transformer is the one that is composed inside, and the reader is the one that's composed outside. The properties are similar because in order to show that this type constructor or this type constructor is a monad, what we do is we swap the type constructors. So let me indicate very quickly how that is done. If you want to show that this is a monad, then you need to implement the flatten function. The flatten function must have the type M, L, M, L, A to M, L, A, which is in type notation could be written like this: M, L, M, L, using the functor composition notation, going to ML. In order to do that, we swap the order of these two, L and M, using a function that is called swap. So swap will be a function of type L, M, A, going to M, L, A. And if you have this function somehow, then you can swap the order. So you, let me move this away. You transform M, L, M, L using swap into M, M, L, L. And then you use flatten on these two monads. So then you get ML. In this way, if you have a swap function, you can define a flatten function for the composition ML. Similarly, for the composed inside, you need a swap function that goes in the opposite direction from ML to LM. And then you can do the same trick. So the swap function, in addition, needs to satisfy certain laws. This will be then necessary to prove that the result is a monad with correct laws. So the laws of the swap function are complicated and not obvious, but you can derive them by trying to prove that the M, for example, here that LM is a monad. You try to prove the law of this monad, for example, the associativity law. Then you find that you cannot prove it unless swap satisfies a certain law. And this is the law that the swap must satisfy. So it must be, sorry, this is actually the definition of the flatten function through swap. I'm deriving the laws for swap. In the next section, I find how these laws are motivated. So I show that these laws are necessary for the proof of monad laws for the transformer. So then the result is a statement that if the function swap exists for any two monads L and M, at this point we don't have to distinguish base and foreign monads. So one of them could be base monad and the other foreign monad. If we have a function like this, which satisfies additionally 4 laws, so there are 2 identity laws and 2 interchange laws, which show that somehow this function is well adapted to both monads L and M, then this composition is a monad. It satisfies the laws. I will also show how swap is directly derived from Flatten. Now, this is an interesting thing because you might say, well, how do I guess this swap? Well, if you have a Flatten for this monad, you can define swap through it like this. Then I study whether they're equivalent. So they're not equivalent unless actually additional law holds. So these additional laws are here. This is additional law for the Flatten function of the big monad. Now, if this law holds, then the swap is correct. So this is an interesting thing that you can actually derive swap from Flatten if you didn't know what it was, or you can derive Flatten from swap. So after this study, you can also look at other laws of monad transformers, because it has lifting laws, and you can show that they hold given the swap function. And also the runner laws. So I'm showing, I'm not going to go through this proof, but I'm showing that the runner laws are satisfied. So I'm going through systematically all the laws of monad transformers, and I want to see if they are satisfied automatically if the swap function satisfies certain laws. And it turns out that you can do that. The swap function has much simpler laws than the monad transformer itself. So this is the summary of this entire investigation, which tells you what laws the swap function must satisfy. For composed outside and composed inside, you need those laws of swap that we had before, and additionally, monadic naturality laws of swap. And so if these laws hold with arbitrary monad morphisms, then the monad transformer is fully lawful. So the 6 laws of swap replace the 18 laws of monad transformers. So this is the story for composed inside and composed outside transformers. So composed inside transformers are limited to linear monads, linear in the sense that they have this form. It's like a linear polynomial in A. So you cannot have any other shape than this. For example, the composition of these two is again linear with different P and Q. So if you can compose them, you still get a linear monad, like a linear function. But you can compose several linear functions, which will again give you another linear function. I go through the laws of swap, so I need to prove that they hold for monad of this type. And that is some derivation where I want to point out I'm using extensively my code notation that I developed for this book, where, for example, this is a matrix that represents a pattern matching function, which is written like this in Scala. So if you compare this function with the Scala code, you see that the Scala code has a lot of names in pattern matching like this, left and right, and left and right. And this notation does not have that. Instead, this notation directly indicates the types. For example, here is the type P, and here's the type Q times LA. So this is the type P here. The value of type P is mapped into this. And the value of type product Q and LA is mapped into this with this function. So this code notation allows me to look directly at what types need to be in the inputs and what types I get in the outputs. And I don't have to write all these names, left, right, for example, and case and so on. I don't write that. I directly write the functions. And the advantage of this notation is that also that the compositions of these functions can be computed using the usual rules for matrix composition. So if you are familiar with matrices and how matrix compositions are computed, then it will be easy to see how to compute compositions of functions operating on disjunctive types or coproduct types. So pattern matching is very naturally represented with matrices in this way. So I prove the laws of swap. So this requires some computation, but these computations certainly need to be done only once if you want to verify yourself that these transformers satisfy the laws. For the composed outside transformers, it's a very different type of monad that has that transformer. It's a generalization of reader. So it's a reader and monads that are similar to reader in some ways. They're selector monad, or sometimes called like that, is this type. It turns out that this monad also has transformers that are composed outside. And then there are other monads. For example, product of two rigid monads is again rigid. Now I call rigid a monad that has composed outside transformers. Now the name rigid is something that I invented for other reasons. I will not talk about this in this tutorial, but this kind of monad or this kind of type class can be used in different ways. It has different properties that are not related to monads. So in any case, these are the examples of monads that have composed outside transformers. So any monad of this sort, any monad of this sort, where the two are composed outside, and the composition. Composition, just like the linear monads, composition of rigid monads is again rigid. So rigid is not something that's widely used other than the reader, but it's interesting that they exist and they could be used. There are some usages of this that I found in the so-called search monad, but I will not go into that. So the rest of this section shows that the swap methods can be defined for the rigid monads and satisfies the laws. So then this is a lot of calculation, which I'm just going to scroll through. Okay, so finally, this concludes the properties of composed monad transformers. So either composed inside or composed outside. So there are some pretty limited classes of monads that have these transformers, and all other monads have other transformers. So we have to look at, for example, monads that are obtained by product. So for example, this monad is a product of ether and reader. What is the transformer for this monad? It turns out it is a product of two transformers. So the ether is a linear monad and the reader is a rigid monad. So for this, the transformer is composed inside, and for this, it's composed outside. The foreign monad is outside, and for this, the monad is composed inside. And so the product of these two is the transformer for the product. And then I show the proof that this is so. Another construction is the free pointed monad. And the free pointed monad is this. So if K is some given monad, then a coproduct with identity is also a monad, and it's called the free pointed monad. So one example of that is the eval monad, the monad that models lazy and eager computation. So what is a transformer for that monad? Now that transformer is certainly not easy. If you know the transformer for K, then you need to use that transformer, and then you have to wrap this entire thing into M. So in Scala code, if you have a transformer like KT of MA, then the transformer for L, so the L of A is either of A, K of A, and the transformer, which you might call LT of MA, must be defined as M. So this is a type definition. So in Scala, you would write like this. Let me try to write Scala more consistently. M must have the argument because it's a type constructor. A equals M of either of A and then KT of MA. So this is the Scala syntax for this. I prefer to write a code notation because it's much more transparent than this. This becomes quite hard to read after some number of nesting. So then we need to prove that this transformer is correct. The proof is quite involved. It is based on a certain kind of swap function, but you cannot use directly the properties of the swap function. Do use it, but it is not the same because it's not a compositional transformer. So there is a certain place where you can use some of those properties, but a lot of the proof needs to be written separately from that. So this is the proof. You have to prove all those things. You see a lot of matrices here because there are a lot of coproducts in the definitions. And so the matrices allow you to look at what types you have everywhere and check the types much easier. The input types match the output types. So these computations finally give you the monad transformer for the free pointed monad. The next construction is recursive monads are free monads and lists, so the main monads that are recursive. So a free monad is a monad that uses a certain functor and is defined like this. It's a recursive type equation, which in Scala syntax, you would write it as type free, and it has a functor parameter and A. Well, actually, you cannot write it as a type, so let me write it as a class. And it contains some value of type either of A, F of free of FA. So in the type notation, it is easier to see that this is a coproduct of A and then F applied to the same type. The monad transformer for this must be defined like this, where M is wrapping this type, but actually M is also inside because we're recursively defining the transformer type in this way. So this would be in Scala, it will be M of either of A and then F of free T of FMA. So this is all this complication. Again, this is a difficult transformer to prove because it has infinitely many numbers of M inside in some sense. So it's a recursive definition that if you want to unwrap it, unroll it, then it will be M composed with this, and then M again composed with this and M. So this is difficult type constructor to deal with. Again, there is this swap function, but this swap function only has a limited usefulness because this is not a compositional transformer. So it's not enough to just define the swap function and prove its properties because it's not a compositional transformer. So the theorems we proved before for compositional transformers do not hold. Now, M and L are a composition of two monads. So you have here a composition, which is M and L, where L is this. So you can prove this, that this is a monad, but this will not be enough. The other laws of transformers will not follow. So we use the swap function to prove that it is a monad, but then we have to do a lot of other proofs. So then this proof is quite complicated, and that's let's see. Okay, and the other recursive monad is list. So for the list, the transformer is defined again recursively, where M is used inside recursively. So similarly, this is not a compositional transformer, and actually we cannot use swap in the same way here because this is not a monad that we can use. It's 1 plus this is not itself a good monad. So we do have some tricks here to prove the laws, and it's quite complicated. So there are some functions that we use to prove this, like this prod function and the comb function and so on. So all this is necessary to prove all the laws of the list transformer, but we do have the proofs of all that. So there's like a comb function. There are all these technical details that I'm just going to skip because unless you really want to study this, and in that case, you need to spend quite a lot of time. I'm not going to be able to explain the details. So these are the proofs, and for the recursive monads, for the constructed monads, and for the linear and rigid monads, all the laws hold. So we have all the runners, we can combine them in any way. They're fully featured transformers. Now, in the next section, I talk about incomplete transformers, because the transformers in this section, such as state and continuation, do not have all the features. They do not have certain runners. and they cannot be used freely as the other monads. So something is weird about these monads. They satisfy the monad laws, but their transformers do not have all the necessary machinery. And the implications for programmers are quite concrete. It's not just some academic laws that are missing. For example, the state monads transformer, it has this shape. It does not satisfy the monad morphism law for base runners, which means that if you want to run the state monads effect in a stack, then you can only, you cannot compose the results of those runs. So what is, let me just talk about this, because that has implications for programming. So imagine you have a stack like this. You have reader, writer, state, reader, writer, state, and then let's say you have some kind of task monad at the end of the stack. Now, suppose you wanted to run just the effects of the state monad and run this into reader, writer, task. For this, you need the base runner for the state transformer, because state here serves as a base monad for this transformer. So you can use the base runner, it exists, but it does not satisfy the monad morphism composition law, which means that if you have two different pieces of your program that you compose, you run the first one, you run the second one, you cannot compose those two results properly. You must create the entire program, the entire monads value of this type, and run only once the state runner. Only in that case, you get the correct result. Now, this seems to be a fine point. Why would I want to do this? But sometimes you want to do this. You want to run partially parts of your program and then combine the results of those runs. So you can only do this correctly if the runners satisfy the composition law, but that is the monad morphism composition law. So the base runner for state monad does not satisfy it. And this is because when you run this, the state has been updated, but this is not shown. The state is not given here. So you cannot run the second part of your program starting from the correct initial state. That is the main reason why this fails. So this really means that you should not be doing this. You should not be running partially when you have a state monad. You should not just run the effects of the state monad in part of your program and then run these effects in another part of your program and then compose the result. You shouldn't write code like this because the state monads transformer does not satisfy this law. So I hope nobody was trying to write code like this, and that's fine. Then you can use the state monads transformer. It's fine in all other respects. It's perfectly well-defined and well-behaved transformer. So here are the proofs that all its laws are satisfied. The second transformer is that for continuation monad. The continuation monad actually has even fewer functions that you can use because unlike all other transformers, this transformer does not use M in a covariant position. So M is the foreign monad, and it's used both in covariant and in contravariant positions, which means that you cannot map M into N and map this into a NR. So you cannot do that. You are not able to do that because and this is a runner foreign runner function, so f run. So there's no f run for this transformer. So which means There are certain things you cannot do. There's no base runner either. So because base runner and foreign runner are connected. Base runner means you cannot run the effects of continuation monad if it's combined with another monad. And you also cannot inject continuation monad into this. So there's no way to inject base, so it's a base lift. A to R, you want to take this and put this into A to MR to MR. You cannot do that. There's no way to do this called B lift, the base lift. So because you don't have these functions for this transformer, they are not available. The type signatures cannot be implemented. It means that you cannot combine the computations in the continuation monad with computations in other monads as freely as with, say, option and list and so on. If you have a continuation monad value, you cannot lift it to the stack where continuation is at the base. You just cannot. So the only way to lift would be if continuation is at the end of the stack. So if you have some monad K, monad L, and then continuation at the end. So then it's not necessary to use B lift. To lift, you use F lift to lift this value into the stack. So that's fine. So for this reason, stacks involving the continuation monad must usually contain that monad at the end, like this. Nothing prevents you from putting the continuation monad in the beginning of the stack, at the base of the stack, but the resulting stack will be not fully usable. You would not be able to lift computations in the continuation monad into that stack. And so, in some sense, you're not able to combine computations anymore. So, the workaround is to put the continuation monad always at the end of the stack, at the deep end of the stack. And the same reason means that monads that are like continuation in some sense, that don't have those lifts and runners, and there are task-like monads like future and task and so on, they're always at the end of the stack. So for people familiar with Haskell, there's an IO monad. IO monad does not have a transformer, and it must be at the end of the stack. So that is the workaround that people use for these kind of monads. So monads whose transformers do not have the base lift means you must put it at the end of the stack. Again, I would like to mention the Xeo library, which takes the approach that there must be just one big monad with all the effects together. So essentially, it's similar to having a task-like monad at the end of the stack. So all the continuation-like functionality, like forking, parallelism, and so on, delayed computations, parallel computations, all that cannot have a fully featured transformer. In some cases, can have no transformer at all. And so those monads have to be at the end of the stack. So the Xeo monad is similar to an IO monad having at the end of the stack, and then some other monad like reader and ether. So here I show what needs to be shown. There's very little that you can have with this transformer, and so there's relatively little to prove. It's relatively easy to prove for the continuation monad. And of course, I'm using all kinds of tricks that I have developed for proving things with the continuation monad, like the flipped Kleist decomposition, which makes computations much shorter, but I will not go into that detail. This is all explained in detail in the book. The generalized search monad has this shape where L is a fixed monad. So this is not a transformer of L. This is a monad that has L fixed. So we have to add M, the foreign monad, to this. So this is the way that we do that. You see it's a similar shape as continuation. M is being used in the contravariant position and in the covariant position. So there's no way that we can have base lifts and foreign runners or base runners. I prove the laws of this monad. This is a little more involved, but that is done here. Finally, a few words about the codensity monad. This is a monad defined like this with a quantified type. Now, the quantified type is a kind of difficult thing to describe. In Scala, this means you have a trait. In Scala 2, in any case, you have to do this. In Scala 3, you can do write it much quicker, but in Scala 2, it means you have a trait with a method that has an extra type parameter. So the code, it has a type parameters F and A, but the run has the R type parameter. So this would be the type definition in Scala 2. So let me make it a little cleaner. Oops, I can't make it cleaner. So what is this monad? I'm not going to discuss. Codensity monad is an advanced tool that is only used very infrequently, but it's a very interesting monad because it's like a continuation monad, except it has this arbitrary type here, which is being quantified. And so, and it's a monad for any F, where F is a functor. It's actually any type constructor, doesn't have to be a functor. It could be not a functor. So it's a very interesting construction that gives you a monad out of any type constructor whatsoever. But this monad is weird. So it's not like a free monad, which also can give you a monad out of a type, any type constructor. This is a very different thing. And so the transformer for this monad, so first I verify that this is a monad. The transformer is defined like this. So it has an M composed with this FR, but only in this way, not F of MR, but M of FR. Because F could be any type constructor, not necessarily a functor. So this transformer also doesn't, like a continuation monad transformer, doesn't have a base lift and other methods. So if you use that monad's transformer, then you cannot really use it. You have to put this monad at the end of the stack. So this concludes the kind of a zoology of monad transformers. As you have seen that every monad transformer is a little different. There are some classes of monads that have similar transformers, like product monads or composed outside, composed inside, and so on. But many monads have transformers defined each time in different ways. So for each monad, a different definition. And I even found some examples where the same monad has more than one transformer. And one interesting example is this. So this selector monad has two transformers. One is this, and the other is this. So the first transformer is fully featured, has all runners and all laws. When this transformer is only half working, so it only has some runners, but not the base runner, not the foreign runner. The second example is the codensity monad, because codensity monad could be itself understood as a transformer if F is a monad. So if this F is itself a monad, then this is a new monad that includes the effects of F, and that looks like a transformer of something, but a transformer of what? It turns out it's a transformer of the identity monad. So it's the identity monad that has two different transformers. It has a standard transformer, which is just a foreign monad, and it has a second transformer, which is a codensity. So that is a kind of weird situation, but yeah, there are some monads that have more than one transformers, but they're not equivalent. So this concludes the monad transformer derivations, and then I have some further material here, which I'm just going to skip through. Like a rigid functor is a functor where you have this natural transformation. Now, this seems to be weird, but turns out you can do certain things with if you have this function. Certain interesting things like R-valued flat map. You can have a flat map that returns several results. If you have that kind of stuff, if R is rigid, then you can use that. So maybe that's useful for something. And there are some other interesting applications, like if you have a program that has this sort of type, so it uses a function f. So you have a program that has the value c, and it uses a function f inside. And you want to replace f with a function of this sort that returns a monad. And the entire function p must be replaced with some function that also returns a monad. So you want to monadify your code. Instead of returning c, you return some r of c, where r is a monad. And instead of f, you return, you use some function that returns r of b. So imagine that you are putting here some monadic effect. You wanted to refactor. Can you refactor? So it turns out that this refactoring is only available if R is rigid. So you cannot in general refactor your program by introducing a monad. In practice, you might be able to always rewrite your program using a monad, but this refactoring cannot be written as a function unless it's a rigid monad. So this is kind of motivation for rigid functors. I show some results about them. Seems to be a new type class that is not well known. Then there is a long section about the lifting of MTL operations, where I take this paper, these papers here, and I prove the statements that are in these papers. So most of that material is just in these papers, but I added a few extra proofs. And anyway, that shows you how to lift a large class of operations MTL style, but certainly this is a very advanced material that I would not try to explain in this talk. So that concludes this chapter. I add a few exercises that look at the properties of some monads. Most of these exercises are quite advanced, and some of the proofs actually have been much longer than I expected. So let me conclude briefly by saying that monad transformers are a very difficult construction. There is not a lot of motivation to use them, even with libraries like MTL and other monad transformer libraries. It remains quite difficult to understand and to use them correctly. The code is, beyond some simple cases, the code becomes hard to maintain because there's just so much hidden machinery in there that you don't understand why your code doesn't compile. You certainly can use it if you are up to this challenge. There are other solutions for combining effects, such as free monads that allow you to combine effects much easier. A certain variation of free monad is, for example, tagless final. That's a different encoding of the free monad. Allows you to combine effects more easily than by combining via monad transformers. Performance of monad transformers is quite bad in Scala because of all this extra machinery that you have to do, all these extra wrappers and type constructors and classes that you have to create just to wrap some types and combine effects. So beyond very simple cases, combining two simple monads like list and either, I would not necessarily use monad transformers in actual code. But monad transformers exist, they are necessary in some cases, and library authors must be aware of all these issues, and in principle must be aware of the laws and limitations of monad transformers. This concludes my tutorial.